Thank you. So I'll be talking about primary secondary resolver membership proof systems, and this is based on two papers, one with Sharon Goldberg, Dimitris Papadopoulos, Larry Raisin, Sachin Vasant, and Asaf Ziv, which was in NDSS this year, and PSR membership proof systems with Asaf Ziv at TCC. So as you can see, these two conferences have quite distinct nature. NDSS has maybe one Israeli participant. TCC has perhaps one non-Israeli participant. So the work has all sorts of aspects. So let's start. What do we mean by primary secondary resolver proof system? So we think that we're really discussing the membership problem, or more accurately, the non-membership problem. So we have a database N of elements from some universe U. And with each object, we associate some information Y. And we want to do lookups in R such that if X is in R, then the answer is yes. And if X is not in R, then the answer is no. Now, and we don't want to leak more information than this. And the problem is that the entity providing the answer is not trusted with respect to correctness. So we really think that there are three parties here. We have a primary who created the set or knows the set, and he's completely trusted, but the primary is basically offline. We have the secondary who does all the talking with the resolver. So the resolver has some element X in U and wants to determine whether it's in the set or not. And he knows the primary's public key, but nothing else. The primary doesn't talk to him directly, not when he knows X. Only the secondary and the resolver talk. So the secondary is not trusted with respect to correctness. So the question is, what can we do in this case? And why is it an interesting problem? The motivation is from DNS lookup. So DNS, domain name server, is the service that translates domain names into IP addresses. So we want to know what is the IP address of example.com. We go to the DNS, and he either says no such thing, or here is the address. And DNS in general is completely insecure. You have no idea whether you're getting the correct answer or no, and the security extension of DNS is called DNSSEC. And it's supposed to retrieve records which are authenticated. And the main issue there is, what do you do with non-existing records? So for things that are in the set, you can simply sign it. The primary can sign them. That's not a big deal. That's why I said the real problem we're interested in is non-membership. But what do you do with non-existing records? How do you prove that something is not in the set? And all the current methods that were proposed actually leak information about the set and allow what's called zone enumeration to actually, you're able to list all the elements in the set as a result of asking all sorts of innocent questions. So here is how the original NSEC works. The primary signs all existing records. It sorts them and puts a link to the next record in the sorted order. It gives all those signed records to the secondary and gives the public key of, his public key is simply the public key of his signature. Given a query X, if it's in the set, the secondary simply returns the signed record. If it's not in the set, he gives X1 and X2 such that X is between X1 and X2, and he has the signed pair X1, X2. So this is the result. You can think of it as the result of an unsuccessful binary search. You show that had you done a binary search on the set, you would have arrived at the conclusion that X is between X1 and X2, and therefore not in the set. And because X1, X2 are signed, you know that it's correct. So here, there isn't any, in terms of correctness, there isn't any problem. As long as the signature scheme is secure, you wouldn't get, even if the secondary is malicious, you wouldn't get any wrong answers. The problem is, after a while, you learn all the records of R. Even with random queries, after a while, you know all of R. Now, you could ask, is this a real problem? Okay. Iftach, I think that's a very good question. So there is much debate because people like Iftach think it's no big deal. After all, it's public information. But I think it's clear that there is a difference between willing to answer questions and revealing everything you know. It's not the same thing. And it's clearly, if you can do it, it's sort of a toehold for mounting more complex attacks. So it's not something you want to give away for free. There are legal issues sometimes to protect host names, and there are EU data protection laws that require it. It could, especially as we go to more household things, it could really reveal things. I mean, whether you have certain electrical items in your home, you don't necessarily want to reveal all your stuff. And now it's a requirement. The IETF wrote the DNSSEC to deal with the issue. So it's a requirement. So clearly it's something you don't necessarily want to reveal. Okay. And so because it's clear that NSEC reveals, allows zone enumeration, people suggested a standard called NSEC 3. And the idea there was that instead of storing X itself, you will store H of X, where H behaves, you know, it's a function that's supposed to behave, let's say, like a random oracle. And you store H of X, and then you do the sorting and everything exactly as before. Okay, except that you do it on H of X instead of X. So now, what you get is H of X1 and H of X2. Instead of X1 and X2, you don't get them explicitly. However, what do you do? After a while, you get all of the H of Xi's, and now you can ask yourself, you don't need to go to the secondary in order, the resolver or the attacking resolver doesn't need to go to the secondary in order to find out whether something is in the set or no. He can do it on his own, and he can do it at a much greater speed, and there will be no trace that he's actually doing it. So at best, what it gives, I mean, if you're optimistic, it gives you an obfuscated, it's as if you publish an obfuscated membership program that allows the adversary unlimited queries. And actually, the specific implementations have been attacked, and people show that you can do zone enumerations. But in principle, let's say you could, if you choose H properly and you think that you know how to obfuscate multi-point functions, then perhaps you will get an obfuscated membership problem. But that's not good enough. So here is where we come. And actually, this work, I wouldn't say started, but certainly one of our meetings was in last year's ICOR. So I thought that it's very appropriate that I talk about it in this year's MOGA. That's when I discussed this problem with Sharon. So what do we have to say? First, we model the problem. We say exactly what do we want from the properties that we want from primary, secondary resolver membership problems. Basically, completeness, soundness, and privacy, which we model as F0 knowledge. I'll define all of them more carefully. We explain why all the current attempts have failed. Nothing like NSEC 3 can work. We can prove it that they cannot work. Basically, we show, the way we show it is by showing that you can construct from a PSR, from a primary secondary resolver proof system, you can construct from it an online public key identification scheme. And then we don't have such we don't have things like NSEC 3, the efficiency of NSEC 3 for identification schemes. And you can even convert them under the proper beliefs, you can even convert them into signatures. And then we suggest various efficient constructions of PSRs. So the constructions we have like 3 strategies for obtaining efficient PSRs. One is based on verifiable random or unpredictable functions. And basically, you can view it as the closest in nature to NSEC3. What you do, instead of h of x that we had in NSEC3, here you compute f of x, where f is a function that only the secondary knows how to compute, but the resolver can verify. So that's one strategy that we have. Another strategy is hierarchical identity-based encryption. Specifically, we use the scheme of Bonnet, Boyen, and Go, and this is the one I'm actually going to describe. And the third one is based on oblivious search, specifically on cuckoo hashing. One advantage it has is that it can be based on very conservative assumptions, discrete log, factoring, nothing more than that. And by efficient, we mean something like order 1 public key operations. And this is as I said, I'm going to describe the HIBE, the hierarchical identity-based encryption one. We also have, and this is more in the line of the verifiable random function, we have construction based on random oracles, which are extremely efficient. One based on RSA. We can base them on the Bonnet, Lin, Shacham signature scheme, or just on plain Diffie-Hellman. But all these things use random oracles, but they use just 1 or 2 calls to these mechanisms. And there is an RFC based on the RSA one. Okay, so so let's see in slightly more detail. What do we have? So we said the primary gets R, executes the key generation. The secondary and the resolver get the public key. And the secondary also gets secret key. So the secondary knows of secret information. Secret information doesn't allow it to cheat. It cannot create false proofs. But it allows him to convince the resolver, the verifier, that he's telling the truth. And as we said before, when the secondary, when the resolver wants to learn whether X is in R or not, he talks only to the secondary, not to the primary. And we said that we want 3 properties, or 4, you could say: completeness, soundness, and privacy. And of course, we want performance, and we can measure performance in all sorts of ways: how many rounds of communication they need, how much information they need to send, and of course, computation, and computation on whose side. And our best system will be like 1 round. The resolver sends a query, gets back an answer. I mean, almost all our schemes are like that, except the cuckoo hashing-based one. And in terms of communication complexity, it's more or less minimal, like 1 element in whatever field we're working. And computation, we said it's order 1, the equivalence of order 1 public key operations. So let's go over the requirements. So completeness, it's quite clear. If everyone acts as they should, then the resolver learns what he should learn. And even if you leak the secondary's key, you do not hurt completeness. Soundness, what we want is that the secondary cannot cheat, cannot make the resolver accept a wrong conclusion. Of course, the resolver can say, I haven't learned anything, but you cannot reach, you cannot cause him to reach a wrong conclusion. And that's true even if the adversary selects the set R and gets the secondary's information, and can select X and can mount any sort of attack, except it doesn't know the secret keys of the primary. Okay, so that's soundness. And now the most interesting aspect is the privacy, which we model as zero knowledge. So we want to say that the adversary does not learn much about the set. So the way we require it is by requiring that there exists a simulator that produces the same distribution of conversation between the resolver and the secondary, having only oracle access to the set R. So, and more than that, it has to be, the simulation has to be online. So the simulator produces a fake public key, and given a query about X, about X by the resolver, he asks an R oracle. He asks an R oracle whether it's in the set or not, and then simulates an answer to the resolver. And there is no rewinding, and what we want is that the transcript he produces will be indistinguishable from a true execution, from a real execution. And indistinguishable could mean either perfect, the same distribution, statistical, close, or computational, that there is no distinguisher that can do it in efficient polynomial time. And actually, the example we're going to see is going to be perfect. Yeah. But yeah, it's completely adaptive. The adversaries, pardon? Of course, on the public key and the answers that you get and everything. And the way you do it, you don't know in advance how many queries you're going to get. You run it, it's sort of a never-ending, it's a never-ending simulation. And there's no rewinding, you just answer. And you are allowed one query to the R oracle for every query that you get. And you have to ask the same question. You cannot ask any other question. So that sounds pretty strong. And there are something we do allow, we call it F0 knowledge. Actually, the example we will see doesn't need it, where you get some function of the set. In particular, you get the size of the set or some upper bound on the size of the set, which may or may not be okay. But we assume that both the simulator and the actual thing, you get this information. And, but again, as we said, no rewinding. So it's quite clear that F0 knowledge implies that you cannot do zone enumeration, but more formally, here is a property that we get, and it will be useful. One reason I'm mentioning it is that it will be useful in our reduction from zero knowledge, from PSR to identification. So we'll use this property. So suppose that we want to break the selective membership. So the adversary can select S and two elements, X0 and X1. The set R is chosen as X plus a random element out of X0 and X1. Okay, so either it's S plus X0 or S plus X1. And then the adversary can ask about any X that is not X0 or X1, and then he should guess which one is in the set or not. And it's not hard to believe, and it's not hard to show that even if you know the size of the set, any F0 knowledge PSR system is secure against selective membership. Okay. So what's known about this before we prove all our stuff? What's known? So there's, of course, all the work I mentioned in DNSSEC, but it's not satisfactory. Then there is the notion of zero-knowledge sets by Mikali, Rabin, and Kilian from 2003. The problem there, they didn't separate into primary and secondary, but between the primary that commits to the set, and then he becomes the secondary and cannot cheat. So it's too ambitious. You don't want, after you commit to the set, you don't want even the primary to be able to cheat. But this seems too strong for our purposes. There isn't any reason not to allow the primary to cheat. I mean, the primary owns the set, whatever. And as a result, even the best constructions required quite a few public key operations, like log U And more formally, we can actually separate them. PSR is equivalent to the existence of one-way functions. There are PSRs if and only if one-way functions exist. On the other hand, zero-knowledge set are equivalent to collision-resistant hashing. And we know these two primitives can be separated, black box separated. So clearly it's not the same creature. Then there is quite a lot of work on verifiable data structure and certificate revocation list and general language for such data structures. But these works usually do not keep privacy. They emphasize only correctness. Okay, so let's start with showing why it's a non-trivial problem, why it cannot be as simple as NSEC3, where all the computation you did was compute h of x, which was a simple function, and do lookup. And for that, we reduce it to the public key identification problem. So we have an authenticator who wants to verify that it's alive and engaging in the protocol. For instance, that it knows, the verifier knows its public key. So think of when you come to the car, and the car identifies your key by such a protocol. And you don't want, even if someone breaks into your car, you don't want them to be able to produce a key. So you want to use a public key scheme. And the security is following the protocol. The verifier should not be able to convince another verifier that it is the prover, the authenticator. So this, well, here is the XKCD look on identification schemes. But of course, there is a bug here in this cartoon, even if you do trust the guy. So there are all sorts of constructions of public key identification scheme using signatures. Signatures are something stronger, using chosen ciphertext secure crypto systems, using the first ones were actually using by Feigefiat and Shamir were using zero-knowledge proofs of knowledge. And all these constructions, they're good, but they're computationally non-trivial. You do require quite a few. You do require, let's say, the order of signature. I mean, in fact, the Fiat-Shamir heuristic says if it's random coins, if the challenge is always random coins, you can translate it under the random oracle assumption. You can translate it into a signature scheme. So it's sort of less trivial. It's certainly computationally more involved than just computing one hash function. And so we claim that the secondary must work hard in the sense that given a PSR system, we can construct an identification scheme. And the work of the online authenticator is similar to the work of the online work of the secondary. And what we're using is really the security against selective membership. And it's very simple. The set that you have contains one element, R, and the identification is choose a random message M, prove that M is not in, and the proof that it's you is by proving that you are not in R. And that's essentially the proof. And this is true even if the secondary is trusted. It's just, it has nothing to do, for this proof to work, you don't even have to distrust the secondary. And essentially, what you can show is that if you can break this identification protocol, then you can break the selective membership problem. And you will be able to guess the bit B. So this explains why all NSEC3 doesn't work and why all sorts of people suggested all sorts of variations on NSEC3. Let's not do it on h of x directly. Let's take h of x and add change the least significant bits of it. Add something small. Add all sorts of points to it, maybe dummy points or something like that. All these things would not work because all these things will not work because they will deal in an identification scheme, which, for instance, under Oracle separation results shouldn't work. And really, the main issue is the secondary has to do something. It cannot be just a lookup. Okay, so let's see a construction based on HIBE, on hierarchical identity-based encryption. So let's start with identity-based encryption, which became famous about 15 years ago, the construction of Bonnet and Franklin, but was suggested by Adi Shamir, I don't know, maybe 30 years ago or more. And we have, it's sort of something in between a public key and a private key. So we have a master who creates a public master key. Using that public master key, everyone is assigned a public key. So in particular, Bob, who has email encrypted using his public key, if he's Bob and he's at the Weizmann Institute, his key is bob@weizmann.ac.il. That's his public key. And if you want to encrypt mail if you want to send him an email, you just send it to bob@weizmann.ac.il. He should have received from Alice his corresponding secret key. Not from, he should have received from the CA, from the certificate authority, he should have received his secret key. Doesn't matter exactly when he receives it, even before or after, but he should have received his corresponding secret key, the one corresponding to Bob. And then he can decrypt all the emails sent to bob@weizmann.ac.il. So that's the IBE, identification-based encryption. And HIBE, hierarchical identity-based encryption, there is another level. You can actually think of everyone is arranged in a tree. And now, instead of just one authority, every node becomes an authority for all its descendants. So every node can generate secret keys of all its descendants, in particular for all its leaves. And so IDs are represented as tuples with up to L coordinates. This should be L coordinates. Each prefix, I1 up to ij, gets a secret key from which SKI can be derived for every I where j is a prefix of I. Okay, so when I first heard of this, I thought of it, it's nice and cool, but I really didn't think of it as perhaps the most useful creature. But as it turns out, it's quite useful. So, so here is a pictorial view. If you know SK of J, you can generate the secret key of I. Okay, you essentially get this node here, this node J here, gets implicitly all the keys of all its descendants. I mean, you can also generate the middle keys, but we're only going to use the fact that it can generate keys for the leaves that are its descendants. Okay, so in the setup, we have a master who generates a master public key and a master secret key. Key generation you generate for every node using the secret key. You generate its own secret key, skj. And using skj and I, you can generate ski. To encrypt, what do you need to know? You need to know the master public key. You need to know the message, of course, and you need to know the identity of I. And then you can generate a ciphertext. To decrypt, you need the ciphertext and you need the secret key of I, and then you get back M. And security will need something actually not the strongest, which makes the construction even more efficient. Okay. And now we claim that you can use HIBEs in order to construct PSRs. So we have our universe, which we think of it as bits, L bits. The primary runs the setup of a HIBE of depth L with binary identities. Now, what you do is for every node in R, for every X in R, you remove all the ancestors of X from the tree T. You start with a full tree, and you remove all the ancestors from T, for every node in R. For every surviving full binary subtree, you generate the key skj and give it to the secondary. And the number of keys, as we'll see, is something like R log U over R. So here is the pictorial view. It's subset cover of non-elements, which is actually something we used in the work Naor, and Lotzpich in revocation schemes. So what you do, here the black ones are elements in R. So here you suddenly removed all the path here, or this node you removed all the things here, and you can cover with full binary trees the remaining ones. So here there wasn't any choice, but you had to give him the specific key because it had so many neighbors which were in the set. But here you have a pretty high node. So, so you cover it, and the cover is something, as I said, something like R log U, log the size of U over R. So that's the number of keys that the secondary gets. Now, the resolver asks for X in U. And the idea is to, what you do in order to prove that you are, in order to prove whether the secondary, of course, if the X is in U, then there isn't any issue. If X is in R, then he just gives him the signature on the elements in R. The only problem is when X is not in R. When X is not in R, what the secondary needs to convince the resolver is that he knows the corresponding secret key to X. If he knows the corresponding secret key to X, that means that X is not in R. So he needs to prove to him that he knows the corresponding key to X. How do you prove that you know the corresponding key to X? Well, there are two simple methods. Either you decrypt, he sends a random encrypted challenge and you send it back. That's one possibility. The other possibility is to give him the key. It's not a big secret. I mean, that's IBE HIBs are supposed to be resilient exactly to such attacks. You give people their secret keys, and yet they cannot learn any other secret key that you didn't give them. Yeah? Signatures would be fine as well. You don't necessarily need encryption. You need, or even identification for that matter. Yeah. You just need to prove that you know something. Exactly. You need to prove that you know you need to prove that you know the white nodes. Exactly. And with encryption, you have all sorts of ways of doing it, either by explicitly giving the key or by simply decrypting. Okay, and that's exactly the scheme. And it depends who does whether you do the decryption, whether you give the key, affects somewhat the complexity of the scheme. It can either, the harder work can either be done by the secondary or by the resolver. So the claim is that this scheme has perfect completeness. I think that's quite obvious. It has soundness, and the soundness comes from the security of the HIBE. That HIBE, if you give all sorts of private keys, you don't learn any other private key. And the more interesting aspect is, why is it zero knowledge? What does the simulator do? Well, the simulator is also extremely simple. You run the setup algorithm for the PSR, and you replace, and you give the, you publish the public key. Given a query X, you ask whether it's in the set or not, whether it's in R or not. You ask the R oracle if it's in the set or not. If it's in the set, of course, you produce a signature that it's in the set. If it's not in the set, You simply generate the private key using the master key. You generate the private key for this guy. Yeah. Right. No, exactly. Yeah, otherwise, if I could sign all the non-members, I would. Exactly, non-members. Okay, so what I claim is that the distributions that we get are identical. So we have perfect zero knowledge in this case. Soundness is only computational, right? If you can cheat, if you can break the hype, then you can cheat. But in terms of zero knowledge, we have perfect zero knowledge, and you're not revealing anything about the size of the set R. So we have perfect zero knowledge, and we're not revealing anything about R. But still, it's not, notice that it's not a zero knowledge set, because the primary can cheat. So it's not zero knowledge. And actually, the construction based on one-way functions is not that different from this. It's the same principle as this scheme. You prove that you can, so there it's more like a signatures. You can prove that you can sign a path, and you just have to do all sorts of things to ensure consistency and everything, but you essentially prove that you can sign a path, and that can be based on one-way functions. So based on one-way functions, you get a perfect scheme which doesn't reveal the size of the set R. And if we had good one-time signatures, it wouldn't even be so disastrous. Okay. I promised you that we have a good hype construction, so let's, the one we found that was most appropriate for us was the one by Bonnet, Boyen, and Go, which uses, not surprisingly, a bilinear map. And a bilinear map means that it's a mapping from, in this case, two groups to another group, which is bilinear in this sense. The setup, so really this, I don't think that I can convey the actual construction, but just I'm going to give you just for impression to see the complexity of things here. Basically, the setup, you select a lot of random elements, the secret key contains a lot of, and also the public key contains like L, the depth of the tree, L elements. And the secret key is the corresponding exponents. To generate it, you really need two L. This should be L, 2L exponentiations. That's to generate the key. To generate a key for a specific node, let's say you choose each one of these guys is either J0 or J1, because we substitute for 0, we generate a random element. We picked two random elements, J0 and J1 from ZP star, where P is the size of the group G. And the secret key of the corresponding ID, I1 up to IK, looks like this. Okay, so you take the H, you raise them to I1, etc. So that looks a little bit complex, but if you look carefully, you see all sorts of things. So the complexity is L minus K plus 1 exponentiations. So that means that the deeper the node, the more efficient the construction is. So that means that generating keys for the leaves is actually quite efficient. It's essentially one exponentiation. But in the setup phase, we need to do that for every root of the full binary tree, which could be more expensive. So the downside of this scheme is that the setup is perhaps more complex than other schemes. And what you do is a secondary, so the secondary gets all the corresponding keys from, for all its full binary trees that it contains. And for each one of them, it costs you something like 4 exponentiation and order L multiplications. And the point is that when computing keys for the leaves of depth, you need only 4 exponentiations because you can group things. You can first multiply the b's with the same exponent and raise them to the power. You simply change the, you simply rearrange the b's so that all those that correspond to 1 are raised to 1 exponent, and all those that correspond to 0 are raised to the other exponent. So it's really very simple. And encryption requires 1 pairing, and you can even get rid of it, and 3 exponentiations plus order L multiplications. And decryption requires, is more involved, and it requires 2 pairing. Pairing is the operation of mapping from the 2 sets to the corresponding, from 2 groups to the corresponding, to the mapped group G1. That's a more involved operation. It's not the end of the world, but it's more involved. Pairing is more expensive than exponentiation, so that requires 2 pairing computation and 1 multiplication. And as we said, it can you can either send the key and then checking that it's the appropriate key is like doing decryption yourself. So either the resolver will have to do the work, or you can, or the secondary can do the decryption, and then so he's the only one who is doing the pairing. So it's up to, that's an optimization that you can do. Okay, so really what have we learned? We learned that denial of existence is a computation non-trivial problem, and in complexity it's similar to signatures. And denial, it's essentially can be done as efficiently as one can expect, certainly if you assume random oracle, and we have a variety of methods like VRF, VUF, HIVE, or cuckoo hashing require a constant number of exponentiations. And many cryptographic primitives can be utilized. Perhaps primitives that you thought are really only of theoretical interest, turns out that they can have a pretty concrete implementation. What we did not discuss at all is what happens if the set changes over time. I'm surprised that Iftach didn't ask that. And so the set changes, what do you do? And each method has, it depends exactly on what method you use and exactly the definition of security you want in this case. Some of the methods we have are better and some are worse. We didn't discuss composition and universal composition. In general, if you have like a 1-round scheme, you get composition for free. So you don't have to worry, but it's not true, but you can come up with counterexample that if you have like a 4-round scheme, then it doesn't necessarily compose concurrently. By definition, everything composes sequentially, but if you have a 4-round scheme, it doesn't necessarily compose concurrently. So let me finish. I don't know, many of you probably know that the beginning of this month, I was still in hospital with a tube in my throat, and I really want to thank the people who took care of me there. These are the doctors, and especially the nurses, who really, I think my reaction was that utility theory has no value when I saw their work. Can't imagine that even seeing me give a talk less than a month after I'm released compensates for everything they did. Don't think you can come up with a utility for that. That would make sense. And this is me on the day I was released. And of course, at the risk of sounding like the most cliched politician, I really wouldn't have pulled through without my family and friends, and of course my wife Dalit, and today is our anniversary. Thank you.